In this video, we're now going to be focusing on arithmetic series. So recall that when you have a series, it's when you sum up all the values in the term of a sequence. Now down here, I have written a very basic arithmetic series. You can see that we start with 1 and then we add 1 every single time. So the common difference is 1. Now, if I wanted to add up all of these numbers from 1 to 100, we don't actually have, well, up until this point, we don't really have a method of doing so. If you wanted to do this, most students would just be plugging into the calculator 1 plus 2 plus 3 plus 4 plus 5 all the way to 100. Now, there was a very famous mathematician when he was, I believe, in primary school in year 5, where him and his classmates, they were put to task in math class, which was to literally add up all these numbers from 1 to 100. I guess the teacher just wanted to keep them busy. So the teacher, expecting to have maybe 15 minutes of free time so that the students could actually add all of these numbers up, this famous mathematician, they said, oh, hold on, I have the answer within a minute. Now, there's a reason why he's a famous mathematician, isn't it? It's because he was able to see this pattern that other people couldn't see. And the pattern that he recognized was that if you were to take the first term and the last term and you add them up, you're going to notice a pattern. Well, in this case, they add up to 101. What about if I get the second term and the second last term? If you also add them up, you also get 101. And you can continue this pattern of adding the one term at the beginning and one term at the end, and you're going to notice that they will always add up to the same thing. Okay, they're not always going to add up to 101. You know, if you get a different sequence, it might add up to something else. It might add up to 50. But the pattern that is happening here is that it is the same sum when you get one from the beginning, one from the end, every single time. So if I wanted to then figure out how to quickly add this up, I would say that the sum is going to be 101 multiplied by how many times or how many different pairs that we have. And if you look at this sequence, at this very simple sequence, you're going to notice that we have 100 terms, but that means if we pair them up, we're going to have 50 pairs. So if we times that by 50, we get 101 times 50 is 5,050. Lovely. Now, us actually completing this is a perfect segue to leading us to a formula for the series of an arithmetic progression. So over here, we have two formulas for the sum of an arithmetic series. The first one is Sn. So we use the capital letter S to refer to a series, and we have a subscript where the n is replaced, which is going to be replaced with a number. So if I wanted S of 7, that means I want the sum of the first 7 terms of the sequence. So this first formula over here is nice and compact. You can see it's given as n over 2, where we have the number of terms divided by 2, multiplied by the sum of the first term and the last term. Now, just think about this. Is this not the exact same thing we did in the previous example? We added the first term and the last term, a plus l, and then we multiplied that sum by the total number of pairs. And the total number of pairs is given by the total number of terms divided by 2. Okay, now this is the first formula, but I'm going to be completely honest, it is not the most commonly used one. Yeah, the reason why is you would only use this formula if you were given the last term of the sequence. Sometimes you do, most of the time you don't. So the most common formula for the sum or the series of an arithmetic progression is this one. I know it looks very intimidating, but trust me, the more you do it, the more you do these problems, it just sticks. Okay, so it's given as the series is equal to n over 2 bracket 2a plus n minus 1d, close bracket. And you can see that n is a number of terms, a is the first term, and d is the common difference. So if you're given the common difference, you use this equation. All right, so let's go ahead and apply them. And then let's also determine which one do I use. So example 1, evaluate the sum of 18 terms of the following series. Now, which one would I use? Well, since I'm not given the last term, then I'm going to have to use the second form. So let's go ahead. we're looking for the sum of the first 18 terms. So I'm looking for S18, and I'm looking for that given that the first term is -2, and our common difference is going to be 7. So if we plug that into our formula, Sn equals to n over 2 to a plus n minus 1d, we are going to get 18 over 2, because we're looking for 18 terms, 2 times -2, plus 18 minus 1 times a common difference of 7. This gives us 1035. All right, great. Next, example 2. Evaluate the series 9 plus 12 plus 25 plus ... plus 225. Okay, now when you look at this, notice how they've given you the last term. So I'm like, yay, I get to use the more simple looking formula. So if we were to write down everything we know that the first term is 9, the common difference is 3, and we know that the last term is 225. Now, if I wanted to plug this into that first form of the series, so we have n over 2, a plus l. What is n? Like, how many terms am I adding up over here? I don't know, it didn't give it to me in the question. In the previous question, they told us that we're finding the sum of 18 terms, so n is equal to 18. But in this case, we're not given that. So what you're going to have to do in order for you to successfully find the sum is you need to use the nth term formula, and you're going to let the last term in that sequence correspond to the nth term. So what I mean by that is when I look at this first term, 9, that's T1. So that corresponds to n is equal to 1. This second term corresponds to n is equal to 2. This third term corresponds to n is equal to 3. And I'm going to let this nth term, Tn, correspond to n is equal to n. So once I let Tn equal to 225, I can solve that equation for n. And then once I find n, I can substitute it into this Sn formula, because now I know what number term this is. All right, so let's go ahead. I'm going to let Tn equal to 225. So the Tn formula is a plus n minus 1d. So we get 225 equals to a, which is 9, plus n minus 1 times 3, okay, where n is your unknown. So you get 225 equals to 9 plus 3n minus 3. 225 equals to 6 plus 3n. 225 minus 6 equals to 219 equals to 3n. Divided by 3, you get n equals to 73. Okay, so that means from this term to this term, there are 73 terms in total. So now I'm going to substitute in that value of n into here. We get 73 onto a plus l. So we get 8,541 for the sum. Example 3. How many terms of the series 20, 18, 16 are needed to give a sum of 104? Okay, so let's dissect this. Especially when you're first starting off this topic, sequences and series, a good tip is to write down what you have and what you want. So we're looking for how many terms, that's going to be your little n, in this series. So a is 20, our common difference, you can see it's going down by 2, so our difference is -2. Are needed to give a sum of 104. So Sn is going to be 104. So let's plug all of that information into our Sn formula, and I have to use the long version because they haven't given us the last term, they just give us the common difference. So if we plug this in, we get 104 equals to n over 2, because we're looking for n, 2 times 20 plus n minus 1 times -2. Okay, now when you look at that, it looks a bit complex, but you just want to clean it up, expand, simplify, and eventually it's going to look like something more manageable. So let's continue to expand what is inside that bracket. So this is going to become 40. Now, there's a -2 here multiplying to n minus 1. So -2 times positive n is minus 2n, and the -2 times -1 is positive 2. Okay. So this will become 104 n over 2, 42 minus 2n. Now, if you expand this out, okay, so if you expand this, you're going to get 42 divided by 2 is 21, so that's 21n. N on 2 times negative 2n is negative n squared. Okay, and that's equal to 104. Now, what do you notice that this looks like? It's a quadratic. Anytime you have something appearing squared, something appearing again, then it's going to be our quadratic. And the way we solve quadratics is you bring everything over to one side. I'm going to bring everything over to the left to make it positive. So n squared minus 21n plus 104 equals to 0. Okay, now let's do some trial and error. Okay, now I found that our two factors are going to be minus 8 minus 13. So product, two numbers that multiply is going to be negative 8 and negative 13. But you can see they add up to negative 21. So we get n minus 8, n minus 13 equals to 0. So therefore, n is equal to 8 or 13. Okay, now we end up with two answers over here. And you might be thinking, oh, we have to remove one of the answers, right? Because how can you have two values of n in which the sum is 104? But actually, you can, because if you look at these terms in the sequence, they're going down in values. So it goes 20, 18, 16, and eventually you're going to reach the negative term, so it becomes more negative. So at a certain point, the numbers will keep going. When you add them, they keep going bigger and bigger and bigger because you keep adding positive values. But then eventually, when you start reaching the negative numbers, you're going to keep adding negative values, which makes the sum go smaller and smaller and smaller. So that's why it actually does make sense for there to be two values of n in which the sum is this. Okay, example 4. The sum of 12 terms of an arithmetic series is 186 and the 20th term is 83. Find the sum of the 40 terms of the series. Okay, so let's go ahead and write down what we know. So the sum of the 12 terms is 186 and the 20th term is 83 and the sum of we're trying to find the sum of the 40 terms. All right, lots going on. So whenever you see that they give you two bits of information and you don't have the sequence, hopefully that raises alarm bells that this is going to be simultaneous equations because you're going to plug in each of these into their respective formulas. And then you're going to have the first term A and the common difference D as the only unknown, right? Two unknown simultaneous equations. Boom, right? And then once you find those two, you find the A and D, you're going to plug that into the SN formula to find the sum of the first 40 terms. Okay, so let's go ahead and set up our two simultaneous equations. So if I substitute this in, I'm going to plug it into the Sn equals to n over 2, 2a plus n minus 1d. We are going to get the sum is 186 of the first 12 terms, so n is 12, a is unknown, n is 12, and then d is also unknown. So you get 186 equals to 6 times 2a plus 11d. 186 divided by 6 is 31, so you get 31 equals to 2a plus 11d, and that is going to be the first simultaneous equation. Okay, now let's find the next simultaneous equation, which is that the 20th term of the sequence is 83. So we're plugging that into the Tn formula because they've given us the 20th term. So Tn equals to a plus n minus 1d. So the 20th term, so n is equal to 20, corresponds to a term value of 83. So we're going to get 83 equals to a is unknown, n is 20, and d is unknown as well. So we get 83 equals to a plus 19d. Okay, now these are your two simultaneous equations. Now, if I want to find a or d, I'm going to notice, because we have to decide which method, right, that none of them have like a variable that is completely in common. Like they both have different a values and they both have different d values. However, the a values are really similar. I'm going to multiply the second equation by 2 to get it to be 2a, and then I can eliminate it by subtracting it. So let's go ahead and do that. Equation 2, multiply everything by 2. If I multiply 83 by 2, we get 166. That becomes 2a plus 38d. And I'm just going to call it equation number 3, just to give it another name. Okay, so now I'm going to take this equation, I'm going to subtract this one. So that's equation 3 minus equation 1. 166 minus 31 is going to be 135. 2a minus 2a goes away, and 38d minus 11d is 27d. So now if I divide them by each other, you get d is equal to 5. Okay, now once you find the value of d, we can easily find the value of a. I'm going to substitute d is equal to 5 into equation number 2. Just this one over here. We get 83 equals to a plus 19 times 5, or a equals to negative 12. Okay. Now, this feels done, right? Because we've done all that work, but just always make sure you answer the original question. It says find the sum of the 40 terms of the series. So now if I want to find S40, we need to plug in everything we know into the SN formula. So over here, S40 equals to n over 2, so 40 over 2, 2a plus n minus 1 times d. So we get 3,420. Perfect. Okay. Now let's do another example. Example 5. Find the sum of the first 12 terms of the following sequence. Okay, so seems pretty straightforward, but what makes this sequence interesting is the fact that we have some surds involved. So we still have to keep in mind that this is still the first term, this here is the second term, and this here is the third term. So let's write down what we have and what we want. So we're looking for the sum of the first 12 terms, so S12. We know that the first term a is 1 minus root 2. What is the common difference? Now, if I had 1 minus root 2, and then the next term is 1, or if I have 1 and then I go to 1 plus root 2, that means that the common difference is a positive root 2 or plus root 2. Okay, perfect. So now if I want to plug it in, we're going to get S of 12 equals to n over 2, 2a plus n, or n is 12, n minus 1 times d. So now let's expand it and simplify. There's going to be 6, 2 minus 2 root 2 plus 11 root 2. 6 bracket 2 minus, or 2 plus 9 root 2. And now this becomes 12 plus 54 root 2. Beautiful. Now here is another application. Example 6, application of the sum of an arithmetic progression. But you're going to notice that our terms are getting quite interesting. They're not just numbers anymore, they're logs. So if I want to find the sum of this series, you're going to notice that I have my first term is log base 3 of 2. This is my second term. This is my third term. And this here, I have no idea what number that is. That's going to be my nth term. So I need to really determine, first of all, is it an AP or is it a GP? And the way I'm going to do that is I'm going to notice that there's a relationship between all these logs, and I'm going to use a bunch of log laws to simplify it in a way where they actually look like really similar to each other. So first thing I'm going to do is I'm going to rewrite the logs. So this one's going to stay the same, but the next one, log 3 of 4, I'm going to change it to log 3 squared. And then I'm going to change the next one to log 3 2 cubed plus dot dot dot. And then the last one, if you want to do trial and error, do 2 to some power until that equals to 1024. That's going to be 2 to the power of 10. Okay, perfect. Now the reason why I'm doing this is there's this log law that says that if you have log to the base a of x to the n, if there's a power on that x, you can chuck that power to the front and it becomes n log a of x. So that means I can bring down every single power down to the front. So this will then become log base 3 of 2 plus 2 log 3 2 plus 3 log 3 2 plus dot 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 plus 10 log 3 2. Okay, and now when it is in this form, is it so much more obvious now that this is going to be an arithmetic progression? Because we started off with log 3 2. To go from there to log 3 2, I'm just going to add another lot of log 3 2. Add another lot to this, don't you get the next one and the next one and the next one? Okay, so that means that my first term here is log base 3 of 2. My difference, I keep adding log base 3 of 2 again. Now, how many terms do I have here? If you notice the pattern that the numbers out front, it goes up by 1. So 1, 2, 3, all the way till 10, then that just means that n is equal to 10. Perfect. So I'm going to go ahead and plug that into our sum formula. So we get Sn, or S10, equals to 10 over 2, 2a plus n minus 1 times d. Okay, this becomes 5, 2 log 3, 2 plus 9 log 3, 2. Or this will become 5 times 11, or 55 log base 3 of 2. Yay, perfect. Good job, guys.